Hey everyone, and welcome to today's Explainer. To kick things off, I want you to just think about something for a second. What are the flawlessly aligned streets of an ancient city, a map of the starry night sky used by early sailors, and a tactile map made of pins and wool for a young boy's bedroom all have in common? Honestly, it kind of sounds like the setup to a weird riddle, right? But the connection between these three vastly different things is absolutely fascinating.
Well, believe it or not, the answer is coordinate geometry. Now look, I know the word geometry might instantly bring back some pretty stressful memories of dusty textbooks and memorizing rigid formulas. But at its core, coordinate geometry is just a brilliantly simple human invention. It's essentially the universal language that lets us pinpoint exact, precise locations in physical space. Whether we're talking about mapping the entire globe or, just trying to find your bed in the dark, it is the invisible mathematical grid that really governs our world.
Okay, let's dive into this. Section 1. Ancient Origins of the Grid.
The sheer historical sweep of this idea is just incredible. We're talking thousands of years BCE, when the Sindhu-Sarasvati civilization was building these massive urban centers with streets laid out in a striking north-south and east-west grid. And they were spaced a perfectly uniform 10 meters apart. Think about that. A merchant could locate a specific warehouse simply by counting units of distance. Fast forward a bit to around 800 CE, and the scholar Baudhayana laid down the real geometric foundations using those east-west and north-south lines. Then we get a monumental leap in 628 CE, when Brahmagupta formalized the concept of zero and negative numbers. Now this was a massive game changer because without negative numbers, mapping points in every direction just wouldn't work. A bit later, Arab scholars like al-Biruni used these very concepts to perfect the astrolabe, which lets sailors navigate by mapping the stars. And finally, in 1637, René Descartes pulled all these global, centuries-old ideas together to formalize the two-dimensional Cartesian plane. He basically proved that absolutely any point could be defined by using just two simple numbers.
All right, moving right along to Section 2, a tactile map for Rian.
To really understand this math, we're going to shift gears from that grand, sweeping history down to a deeply personal, micro-scale story. The source material introduces us to a young boy named Raishian. It's the start of the school year, his family has just moved to a new city, and Raishian is visually impaired. As you can imagine, navigating a completely new physical environment is a massive, daunting challenge. But his older sister, Shalini, who had literally just finished learning 9th grade coordinate geometry, decided to use those exact ancient mathematical tools we just talked about to help her brother orient himself. And what she did brilliantly illustrates a real-world application of this math. Shalini built a tactile map. She created a rectangular grid mapping the floor of his room, precisely scaled so that 1 centimeter on her map equaled 1 foot in real life. She used physical pins to mark out the corners of objects, like his bed and his wardrobe, and then connected those pins with thick wool. By feeling the pins in the wool, Rayan could use his fingers to mentally map out the spatial relationships of his brand new room before he ever even stepped foot inside it. So let's get into the mechanics of this. Section 3, the Cartesian plane. So how exactly does a tactile map like that work mathematically? Well, the crucial point is establishing a foundation. To map any two-dimensional space, we need two reference lines that meet at perfectly right angles. First, we have our horizontal line, which we call the x-axis. Then we have our vertical line, called the y-axis. And the exact spot where they cross, that is our starting point. We call it the origin, mathematically represented as 0, 0. From this one single anchor point, literally every other location in the room, or for that matter the universe, can be exactly defined.
Now, just look at how perfectly these concepts align. Notice how the abstract mathematical grid maps directly onto Rian's room.
Shalini essentially turned the physical walls of the room into her axes. The bottom wall of the room serves perfectly as the horizontal x-axis, and the left wall of the room acts as the vertical y-axis. That makes the bottom left corner of the room the origin. Suddenly, this totally abstract concept becomes a literal, physical space you can walk right through.
Which brings us to Section 4, Navigating Two-Dimensional Space.
So, how do we give a precise address to a specific object? We do it by overlaying Rian's room with exact coordinates, written as numbers inside parentheses. Take a look at the top left corner, marked as point C. Its coordinates are 0, 10. The first number is always our x-coordinate, representing the perpendicular distance we move along the horizontal axis. Since it's 0, we don't move to the right at all. The second number is the y-coordinate, the vertical distance, so we just move 10 feet straight up the left wall. Every single corner of the bed, the wardrobe, the door, they all have specific, exact numerical addresses derived simply by measuring how far across and how far up they are from our origin point.
Now, in Rian's room, we're only moving right and up, which means our numbers are always going to be positive. But remember Brahmagupta formalizing negative numbers earlier? By extending our axes backward past 0, the axes slice our two-dimensional plane into 4 distinct quadrants. In quadrant Y, both numbers are positive. If you move left into quadrant 2, your x becomes negative while y stays positive. Down in quadrant 3, both x and y are negative. And in quadrant 4, x is positive but y is negative. This incredibly powerful concept is what allows us to map points in every possible direction infinitely. It's literally the basis of all modern navigation.
Okay, let's move to Section 5, Calculating Distance Between Points.
Navigating straight along a wall is super easy, right? You just count your steps. But let's pose a practical problem for Rian. What if he wants to walk directly from his wardrobe over to the edge of his bed, and that path forms a diagonal line across our invisible grid? How on earth do we calculate the exact physical distance of that diagonal line just by knowing their grid coordinates?
Well, here's where it gets really interesting, and it takes us right back to ancient geometry. To find the lengths of a diagonal line between any two random points, we simply draw a right-angled triangle. You take your start point and your end point, and you just drop a vertical line from one and a horizontal line from the other until they meet. It's that simple. Think of it like mapping out a simple walking path. Step 1, calculate the horizontal distance by subtracting your x-coordinates. Basically, how far right did we go? Step 2, calculate the vertical distance by subtracting your y-coordinates. How far up did we go? Once you have the lengths of those two straight sides, step 3 is just connecting the dots using the Baudhayana-Pythagoras theorem. You square the two straight sides, add them together, find the square root, and boom, you have the exact length of your diagonal path.
And that leads us to this beautifully elegant formula. Distance equals the square root of the change in x squared plus the change in y squared. Now, I know it looks a bit complicated written out like that, but it's really just a recipe. It's the ancient geometry of Pythagoras and Baudhayana mathematically married to Descartes' grid system. And it works perfectly every single time, whether you're mapping the distance between two stars light years apart, or just calculating the exact number of steps Rian needs to take to reach his bed safely.
So, I want to leave you with this question to ponder. Could understanding the invisible math around us be the key to making our physical world more accessible to everyone? We've seen today how coordinate geometry is so much more than just rigid equations on a page. It's a deeply historical, profoundly human tool. From the ancient cities of the Sindhu-Sarasvati civilization to a tactile map in a modern teenager's bedroom, this mathematical framework allows us to understand, organize, and navigate space. It proves that by understanding the invisible math around us, we really can make our physical world more manageable and welcoming for everyone.
Thanks for joining me on this explainer, and keep looking for the math in the world around you.